This is the most important part of the three-part video sequence, as knowing what the atmosphere is doing right now is important for prognosing what the atmosphere will be doing down the road during the winter season. First, we will take a look at the tropical Pacific sea surface temperature anomalies, indicating that with this blue, there is an area of cooler than normal sea surface temperature anomalies present. This would indicate that we have a neutral negative to a weak La Nina ENSO state, indicating that trade winds are stronger than normal across the tropical Pacific. In addition, looking at the 30-day average outgoing long-wave radiation anomaly, we can see that the highest OLR anomalies are focused right by the dateline over the last month or so, indicating that we do have a west-based La Nina taking place. This is important as the outgoing long-wave radiation tells us that with higher values relative to average, as indicated by these oranges and blacks here, show that you have less convection taking place, less cloudiness, and therefore sinking air as a result further west relative to areas further east. We can look in the past to see when this has occurred and notice that we do have quite a few years listed here. With these purples, that indicates areas where outgoing long-wave radiation values were higher relative to average, indicating you have lower convection, lower cloudiness, and sinking air taking place as a result. This indicates we have a west-based La Nina as shown in this composite right here. Notice that the U.S. as a whole is warm relative to average, which is important to note as we do have a west-based La Nina, as indicated by the highest sinking motion anomalies being further west relative to further east. We do have a weak La Nina, however, and the composite for that is shown right here, as northern parts of the United States are generally cooler than normal during a La Nina, whereas southern parts are generally warmer than normal. This bubble of high pressure generally corresponds to the strength of the La Nina, meaning that stronger La Ninas generally mean a larger southeast bubble of high pressure, which generally means that this area of warmth becomes much more expansive with a strong La Nina as opposed to a weak La Nina. Looking at how those upward motion years listed before can change the Pacific North America pattern, we have the current Pacific North America pattern from mid-October to mid-November here. Notice we have a few distinctive features that are important to look at in order to determine if some of those upward motion years have any similarities to this year, and therefore may be crucial in showing how the Rossby wave pattern will evolve down the road. Notice we have this ridge just northwest of Hawaii here, this trough south of Alaska, and this warm bubble across the central United States, which has been responsible for the very warm autumn across much of the United States. We also have troughing just west of Alaska and troughing just east of the East Coast. When we look at four of the upward motion years that we described before, notice we have a very similar looking pattern. We have that ridge northwest of Hawaii, the trough just west of the west coast, that ridge bubble just east of this trough right here, troughing just west of Alaska and troughing right off the east coast. This tells us that these 4 years may portend to what the winter pattern may show as a result of where the best upward motion is taking place and how the hemispheric Rossby wave pattern has evolved in these years relative to other years during the autumn. Also interesting to note is that the quasi-biennial oscillation, the QBO, a measurement of the wind direction and wind speed in the tropical stratosphere, is into uncharted territory. And by this, we have 2 consecutive winters in a row where we will most likely have westerly winds in the tropical stratosphere corresponding to positive QBO values. We had a time period in the early 1950s where we had persistent easterlies taking place as indicated by protracted negative QBO values, but we've never seen consecutive winters where the QBO has been positive. So we are really into uncharted territory here. And looking at what some of these winters have looked like with low solar activity, which we are currently seeing right now, with positive QBO values, we get this depiction right here. I really want to focus on this area in Western Canada, though, as this trough right here corresponds to a negative Pacific North America pattern, and this bubble of high pressure into Greenland corresponds to a negative North Atlantic oscillation. It is important to note that these 3 years right here do not show any other similarities besides the positive QBO and low solar activity. Thus, they were not included in the analog package. This year, 2010 to 2011, showed many similarities to this year and thus was included in the analog package. Positive QBO and low solar is important for determining how the hemispheric weather pattern will evolve, but other factors are also important as well. And given that these 3 years did not show any other similarities besides the positive QBO and low solar, they were not included in the analog package. And as we mentioned before, caution should be taken with this depiction here, because we are really into uncharted territory of 2 positive QBO winters in a row. This has never been seen in the 60 years of observing and reanalyzing the QBO. And what's really important to note, though, is that even though these winters did not show any other similarities, we had a pattern during October to November for these 4 winters that looked very similar to what we saw during autumn. This shows the October to November composite for these 4 years. And you can see that we have this dip in the jet stream right off the west coast, this positive into the central part of the United States, the positive northwest of Hawaii, and the negative just east of the east coast, indicating that it is not totally unfounded to show a composite of these years, as the pattern was relatively similar to what this year looked like in the autumn. The Pacific Decadal Oscillation is a measurement of these warm waters in the northern Pacific. This warm horseshoe right here indicates a positive Pacific Decadal Oscillation, whereas this cold horseshoe in the northern Pacific indicates a negative Pacific Decadal Oscillation. While this would generally signal a positive Pacific Decadal Oscillation, the values of the Pacific Decadal Oscillation are actually negative. And this is because the sea surface temperature anomalies are actually a reflection of the atmospheric pattern. And the atmospheric pattern has been conducing itself in such a way that is consistent more so with a negative Pacific Decadal Oscillation as opposed to a positive Pacific Decadal Oscillation. So this warm horseshoe is a little bit misleading relative to what we are dealing with for this year. The Atlantic Multidecadal Oscillation is seen here, and the Atlantic Multidecadal Oscillation is positive, generally positive, and generally expected to remain positive for the winter. This mirrors that warm horseshoe-like effect in the Pacific, except the Atlantic Multidecadal Oscillation shows that horseshoe-like pattern in the Atlantic. And so, what does this kind of oceanic oscillation composite entail for the winter season? It shows that we have a cooler Midwest into Northwest, and we have a southeasterly ridge, which is consistent with La Niñas and colder water here, favoring troughs into the west, whereas the warmer water favors more ridging, as that ridging really feeds back off of the warmer waters off the east coast. One last factor to take a look at is the Snow Advance Index, and this measures the rate of snow extent increase south of 60 North in Eurasia during October. The tendency for a stratospheric high does represent large increases in the Siberian snow cover extent. And therefore, once you get this Siberian high, you generally lead to this kind of Arctic oscillation pattern, according to research done by Dr. Judah Cohen. And this is a negative Arctic oscillation right here. This is a positive Arctic oscillation here. This is a negative Arctic oscillation, indicating that with a positive Arctic oscillation, you have cold air locked by the pole, whereas with a negative Arctic oscillation, you have more cold air into the mid-latitudes. So a high rate of increase with this snow cover in Siberia south of 60 North generally corresponds to this phase of the Arctic Oscillation. And one of the reasons for why we had such a high snow advance index year is because of what is currently taking place in the Arctic. This also is into uncharted territory. We have never seen as large of a decrease this late into the Arctic season as with this year. Notice we are about 1 million square kilometers now lower than the previous record low in the Arctic. This is releasing lots and lots of latent heat into the atmosphere, because once you have less sea ice during the summer, you have more open water, and therefore the amount of energy you have that gets released increases the more open water you have to freeze during the fall. And as a result, notice how warm those temperatures in the Arctic Basin are during the fall as a result of all that latent heat being released, with all that additional freezing that is now taking place this year relative to previous years. So this is really important also for snow cover too, as those really warm anomalies have generally corresponded to positive snow cover anomalies over Siberia. This is a nice graphic compiled by an American weather poster indicating which years corresponded to which El Nino state. And you can see 2016 was actually third highest for the snow advance index. But we're only going to be taking a look at the years that are either neutral or La Nina based. When we do that, we can see that we have the same kind of general pattern that we saw with the negative PDO and positive AMO. We have this cool over the central part of the United States, and we have a warm bubble near the eastern part of the United States, although it is less of a warm signal across much of the mid-Atlantic than the negative PDO and positive AMO composite was. And so how do these observations fit in with the winter forecast? As in, how do we weight each of these factors into the analog package? And we'll be doing that in the next video, which will be out shortly.